Okay, let's get started. Good morning. Welcome back. Happy Friday. So, a couple of things of note on the calendar. Today, we're going to talk about something called integration by substitution. That technique is so important, we're going to talk about it again next class. So 2 days on this one section called substitution. Quiz number 2 is due today, right now, right here. Throw it in the folder. This is the one where you graded it already. This is me outsourcing my job. So throw your graded quiz right there in the folder for me. I'll give it back to you after I record the grades. Our next class is not until Wednesday. Monday is Washington's birthday, so we have no day classes on that day. Go out and honor our first president by buying a mattress. On Wednesday, which is our next class, project number 2 is due. Does everybody have a copy of project 2? We got snow days and then like not quite snow days. It should have been snow days. I'll make sure everybody has what they need. Everybody has project 2? Yeah. Okay, so project 2 is going to be due Wednesday, which is our next class. On Wednesday, I will also hand you project 3. Any questions on the calendar? Okay. As this course rolls along and as your other courses ramp up in difficulty as well, at some point, many of us are going to need to make some choices about what to do when you cannot do it all. And so I just want to make sure that you are making the choices that I want you to make when you cannot do it all, because I recognize there are a lot of responsibilities, a lot of things I'm asking of you in this course. So up here at the top level of priority are quizzes, because they're due when they're due, and I don't have a lateness policy on them. It would be like if you didn't show up for an in-class quiz and then tried to come in later on. I'm not really sure what to tell you. So the quizzes are due when they're due, like right now. The projects, I do accept them up to a week late, but there are penalties associated with them, and so you kind of want to have the projects up there as a priority as well. Studying for tests, way up there. The tests are going to be worth a lot no matter what grading choice you make. But way down, far down below all of those priorities is homework. And so I don't want you to get the impression that just because I walk around before class and write a little 4 in a box here, that, oh, good God, if I do nothing else, I have to make sure I do the homework so I get my 4. That's not the most important thing. The point of the homework is to make sure you understand the material. It could be that you can understand the material by doing a quarter of the homework. And if that's the case and you cannot do everything, then do the projects and do the quiz and do your best to prepare for the test, and accept a slight penalty on the homework, which doesn't count for much at the end of the day in terms of your overall grade anyway. All right? It's clear what the priorities are? Okay. All right, so we got that. Did everybody get the new calendar which I gave out last time? Everybody has an updated calendar? Yes? Yeah, rip off the quiz and throw it right in the green folder for me. Okay, so all of those announcements out of the way. We're just going to take one quick step back to page 55 and make sure that we get the ultimate conclusion of the second fundamental theorem of calculus activity that we did last class. So here on 55, I want to take a look at 15. I think many groups got to 15, but not every group did. And so I just want to make sure everybody sees this important result. So we're going to find the derivative of the integral from 1 to x of t cubed dt. Let's give it a shot. So we're going to work from the outside in. If you've already got this written down, you don't need to copy anything. So finding this integral involves taking an antiderivative of t cubed. That's our basic power rule, t to the 4th over 4. Do we need to put the plus c? Not here, because this is a definite integral. So we're just going to choose the plus 0 because that's the easiest thing to do. And then we're going to put a 1 and an x on the right-hand side. And that notation means plug in top and bottom and subtract in the right order. So I haven't done this derivative business yet, so I'm still doing my plugging in. So t becomes x, so we go x to the 4th over 4 minus, and then t becomes 1 to the 4th over 4. And now finally, the outside thing has been just waiting for us to take a derivative. So we take a derivative of x to the 4th over 4. You could use the quotient rule, but you don't need to. That 4 is just a constant multiple, so it stays. Derivative of x to the 4th is 4x cubed. What's the derivative of this minus 1 to the 4th over 4? 0. It's constant, so it disappears. And ultimately, we get x cubed as our final answer. And so even before attempting this problem, you might have recognized that we're doing something that we're immediately going to undo, right? The integral says essentially just take an antiderivative, and we have to plug in, and then we take a derivative, so we expect cancellation. So take a look at the original function, the original integrand, t cubed, and the final result, x cubed. It's not a copy, but the t became x, yeah? And that's what the second part of the fundamental theorem says. If you have something that looks exactly like this, which is a very, very specific form, the derivative of the integral from a number up to x, that's how specific it is, then you get to use our little shortcut, which says, oh, all you got to do is change the t to an x, you're done. And so as a quick example here in 16, it is exactly that specific form, the derivative of the integral from 6 to x of cosine of t dt. I say, oh, it's the second part of the fundamental theorem of calculus, and I just change this t to this x, and I'm done. So the answer here is cosine of x. And we're not doing any derivatives, and we're not doing any antiderivatives. We are taking advantage of that theorem, okay? And then there are little variations on the theme. For example, part A in 17. It looks almost exactly like the ones we just did, but there is an important difference. Two variables? Oh yeah, the b does appear. There's a b in a couple of places, but that's okay. All we're doing is changing all the b's to an x. Yeah, the x is in the wrong spot. Our theorem is very specific. It's a number in the lower limit and an x in the upper limit, a variable up there. And so what we need to do is just a tiny bit of work to get it so it looks exactly like our theorem. So I'm going to write this down. It is not equals at the moment, but I'm just going to swap them because that's what I want it to be. But I got to pay for it. What do you do when you swap the limits of integration? Is you put a negative sign. So the thing in the brackets originally is equal to the thing in the brackets at the end, right? I swapped them, and at the same time I put a negative sign. And I say, great, a negative sign inside of a derivative is just a constant multiple. I can pull it out in the front. I'm not going to rewrite it, but I'm now prepared to use my theorem because the limits of integration are in the right order. Number on the bottom, variable on top. So my final answer, change the b's to an x, both of them, x over cosine x. But then that negative sign is just lingering in the final answer, right? Okay, and the last one we'll do together, let's take a look at part C. So derivative of the integral from 21 up to 5x squared minus 3x of w plus ln of w dw. So again, almost in our basic format. But up here where I'm expecting an x, it's something more complicated. It's a function with x's in it. So this is the chain rule, because we have a basic derivative rule that tells you what to do if it's x. So you're going to apply that same basic derivative rule as if this thing up here at the top were x. So the basic derivative rule says change all of those w's to x, but it's not x. It's that complicated stuff at the top. So w becomes 5x squared minus 3x. I'll put it in parentheses. It's not really needed. Plus ln of w plus ln of, again, it's not x. It's that stuff at the top. And that appears to be the rule, right? That's us naively applying the rule, even though it's not x. That's what we would have done if it was x. But the chain rule says, okay, once you've applied the rule naively, what do you need to do if it's not just x? Is take the derivative of that stuff, the stuff that we were treating like x. And you just need to multiply by the derivative of the stuff. Derivative of the stuff. So what is the derivative of that stuff that was normally x? 10x minus 3. And that's our answer. Okay? That's the chain rule. Apply your normal derivative rule as if it were as simple as x, and then you pay for it by multiplying by the derivative of the thing that isn't as simple as just x. So fundamental theorem of calculus part 2, that's the heart of it. And I think this is a really nice segue into what we're going to do today anyway, because we're going to talk about the chain rule, but in reverse. Any questions before we finish up here? Okay, so we're going a few pages away, 58. Daily summary. In this class, we learned the technique of integration by substitution. This technique is the most important integration technique by far. We are going to have a number of integration techniques after this one, but that does not diminish the importance of this one. This is far and away the most important integration technique. Number one, we will learn many techniques for finding antiderivatives this semester. The most widely used of these techniques is the one we covered today and next class. In the same way that the chain rule allowed us to differentiate many new functions last semester, the substitution method allows us to anti-differentiate many new functions this semester. Spend time in the coming weeks reviewing the material from this section. If you don't get good at substitution, much of this semester will be a struggle. No pressure. All right, number two, many integrals that we encounter will not initially be one of the few forms that we've studied so far. We have a very short list of things that we can find antiderivatives of. It's just a very brief table. However, there's a powerful technique known as the U-substitution method that will convert a bunch of unrecognizable integrals into easy-ish integrals, easier, I guess I should say. So we're going to try number three, but I'll cross something out in purple. Go ahead and cross out the thing in purple. No, getting rid of the negative, getting rid of the fraction, and the plus sign. We're just going to integrate that second fraction. Okay, don't worry about frantically writing out all the steps. There is a step-by-step process on a reference sheet that we'll look at in just a couple of minutes, all right? So just focus on big picture ideas here, not all the little nitty-gritty details. So I'm going to just copy my original integral here. And first ask if this thing is in our short list of integrals. The answer is no. I mean, I'll recite for you the very few things that we can anti-differentiate, and I can recite it because it's so short, it's hardly going to take any time. We can deal with x to a power. We can deal with e to the x. We can deal with a number to the x. A to the x is what we called it. We can deal with sine of x. We can deal with cosine of x. I think we had, what else did we have in there? We had a 1 over x. Yeah, secant squared is on our list as well because the derivative of tangent is secant squared, which is one that I just asked you to memorize, but we don't officially have that one at the moment. It's a very short list, and nothing that looks like that is exactly on our list. So we're going to do some work. First thing we're going to do is split this up into two fractions. So do we buy? This is just algebra, no calculus here. These two guys are equal. Pull the numerator part, two fractions. Okay, and so we're gonna split this guy up into two integrals because we know addition and subtraction work really nicely with integrals. Okay. The second integral is actually pretty much on one of our lists. Can somebody find the right page with the list of basic antiderivatives? It might be page 5. Can somebody check there? It's essentially just arctan. And if you don't have it memorized, just jump to page 5 right now. I think I'm quoting you the right number. But on page 5, I think we have a short list of antiderivative formulas. Yes, we do. And so if you look at the last one in that first table on page 5, 1 over u squared plus 1. Everybody see it? 1 over u squared plus 1 looks an awful lot like this, and I'm not worried about the 3 because the 3 is a constant multiple that I can imagine outside of the integral. So this guy is easy. This is really just 3 times arctan of, come on, 3 times arctan of x plus a c. Done. That's the easy one. It's the other one that's the tough one. 9x over x squared plus 1. How come it's not just 9x times arctan? Yeah, because that x in the numerator, you can't treat the 9x like a constant. You can't pull the 9x outside of the integral like we did with that 3 in the other integral, right? Constant multiples come outside. Variables in no way, shape, or form come outside of integrals. So it's not as simple as just pulling the 9x out. We cannot do it. Can we do something like this? Can you imagine taking the integral of the top and taking the integral of the bottom and just dividing them, just leave it like a fraction? And the answer is no. You might think, well, that's one of our rules. You can look carefully. It's not. We can split integrals up with subtraction like we just did here. We can split integrals up with addition. But there's no rule for splitting up integrals with multiplication. And there's no rule for splitting up integrals with division. And even if you tried, so don't copy this down because it's dead wrong, but if you tried to do antiderivatives on top and bottom separately, so upstairs becomes a 9x squared over 2, right? Add 1 to the power and divide by the new power. Downstairs, x squared becomes x to the third over 3 plus 1 becomes x, 1x, right? Okay, so suppose that we think, hey, maybe that's the answer. Well, we can easily check. What would you have to do to that to check if it's the right antiderivative? Let's take a derivative. And what are we hoping to get? Hoping to get the 9x over x squared plus 1. But what derivative rule all of a sudden rears its ugly head on this green thing? It's quotient rule. And I don't know about you, but I was not at all thinking quotient rule when I was doing the green. And so certainly when I do the quotient rule, I'm not going to miraculously get back up to this thing, right? The quotient rule is complicated. So it just is, it's just not easy. So new technique. Here we go. We are going to do this new thing called a U substitution. We're going to let U equal the stuff in the denominator. We'll talk about how to decide what you should let U equal in a little bit later on today. But for right now, just bear with me. We're going to take the derivative of that thing right there. I'm going to use good notation here. Du dx is going to be my notation every time. Derivative of x squared plus 1, ux. I am going to solve that equation for dx. The dx isn't really a quantity. This is just part of notation, right? Du dx is just notation. It means take the derivative of u with respect to x. But we're going to treat it like a fraction. Like du and dx are these completely separable quantities. So I'm going to multiply both sides by dx. So the dx moves over there. And I'd said the goal was to solve for dx. So what should I do to both sides? Divide by 2x. So we get du over 2x equals dx. It's a very strange looking equation, but it's going somewhere useful. So the step there is to solve for dx. Again, the steps will be written out in English on our little reference sheet, which we'll look at in a few minutes. Then we're going to go back up to our integral, and we're going to start replacing. So this thing right here is going to become integral of. First thing we do is get the u in here in its simplest form. Where was the u in this original integral? It was in the denominator. So I'm just going to do the bare minimum writing that I need to get a u in there. Not copying everything, just getting a u, which necessitated that fraction line. Then we are going to substitute for the dx, which we now have a convenient expression for, right? There's a dx in the original, which we are going to change right now to a du over 2x. So dx, do lots of colors here. This dx becomes du over 2x. So far, so good. And then we're going to copy into our new integral anything that hasn't been replaced yet from the original integral. So what's the only thing that we haven't rewritten is the 9x, right? Everything else has made its way down here. So I'll keep it here in black, 9x. So it looks like a terrible mess, but at least you should buy that it's equivalent to the original. Every piece in the original has been either copied or substituted for. Fair? Okay, now we cross our fingers and hope that all of the x's that remain in this thing disappear. In this case, there's an x on the top and an x on the bottom. I didn't write it, but there's a little multiplication sign there. So I can cancel them, can't I? X and x cross off. So this guy becomes integral of 9 over u times du. Where's my 2? 2 over 2. By just crossing off the x's. Cancel, cancel. And well, that looks a lot nicer than most of the integrals that are up on the board right now. The 9 and the 2, what can we do with them to make this even cleaner? Well, right outside. What number do I put outside? Single number? 9/2. That's what comes outside. Just keep things where they were. So I got a 1 over u du with a 9/2 in the front. And 1 over u du is mercifully one of like the 10 integrals that we can actually find. What's the antiderivative of 1 over u du? is ln of u. It's one of the few things that we can do. Wonderful. So the 9/2 is copied in the front. This guy becomes ln of u. We're still putting absolute value. We haven't talked about why, but that's just going to be part of kind of what we've memorized here. Stick on our little plus c. We'll talk about the absolute value next class. And that's it. Yeah, Dave. Yeah, we can't do that. So, I mean, like, it looks like it's done. But look, the original problem was 9x over x squared plus 1, right? This is a very strange answer to leave, ultimately. U is something we invented to help us out. You can't leave it. It's an intermediate, but it has to go back to x. So the last step is to just change the u to whatever you defined u to be way back in the beginning. What was u equal to? X squared plus 1. And then we'll put our little plus c there. So that's it. 9/2 ln of x squared plus 1 plus c. Sam.
So, I'm not understanding is that between those two steps where you changed when it was still 1 over u, it wouldn't be ln
From which one? From 1 over u?
Yeah, if you have 1 over u.
So let me, all right, so I need a little more space here. All right, so you're saying at this point, and there was the 9/2 in the front, which we'll ignore. So you're saying at this point, if we go back to what it was, which was an x squared plus 1, then you see an arctan, not an ln. I agree, but you got to change the du as well, and it doesn't become dx. What was du equal to from our calculation up there? Was 2x dx, which is not arctan anymore because of that x. But in fact, I really like the question because it gives us a chance to check our answer. Like, is our answer reasonable? Suppose that you take the derivative of this, ignore the absolute value. The derivative of ln of x squared plus 1, 1 over the stuff, right? 1 over x squared plus 1. Chain rule comes in, times the derivative of the stuff. So times what? 2x. And look, it's exactly what Sam has pointed to. It's 1 over the stuff times the 2x. We did all of that work just so that we could get our integral to look like the chain rule would have given us. Chain rule wouldn't have given us that 9. Chain rule wanted a 2 there. So we had to do work, and the 9/2 is the work that we had to do to build something that the chain rule would have given. Good. Okay, so final answer, I'm not going to write it down, but we did 2 separate integrals. The final answer would just be the 2 answers subtracted at the end, right? So this yellow stuff minus the 3 arctan of x. Just a single plus c at the end. We're just smushed together the 2 constants. Okay. So, yeah. All right, so let's take a quick look together back to page 6. In fact, back to page 5 first. So page 5 is an integration formulas reference sheet. If you have other pages in front of page 5, those are just extra copies of the quiz that you just turned in. You can rip them out and recycle them or frame them, whatever you want to do, but you don't need them anymore for our purposes. The next page on the top of the packet should be this page 5. So this is a reference sheet that you will use on upcoming tests in the final exam. So it's got our short list of integrals that we can do. Notice that these guys all have u's in them as opposed to the x table that we came up with a few classes ago, because oftentimes it's going to come from a u substitution. So that is good. And then on the next page, which is the back, which means you will also have this with you on the test, is essentially the step-by-step process for u substitutions. So you'll have this with you on the test. So very quickly, we're just going to run through this particular integral, brand new one. Integral of x squared times 3 plus 4x cubed all to the 5th dx. So step-by-step process. First, you're going to let u equal some stuff. How do you know what stuff to let it equal? Well, if there's something in parentheses, oftentimes that's a good first attempt. It's not always going to work, but in this case, the thing that I see in parentheses is 3 plus 4x cubed. So we're going to try letting u equal 3 plus 4x cubed. Then we will take a derivative of that thing. Derivative is 12x squared, so that's written here in the next line. U dx equals 12x squared, right? And I just want to point out at this moment that in this one problem, we're doing a derivative. But ultimately, what is this problem asking for? An antiderivative. And so we really need to know our derivative and antiderivative rules cold, because in most antiderivative problems, you are also going to be doing a derivative. It's really easy to get them confused, to go the wrong way. Okay, so we've got our derivative with good notation. We're going to solve for dx by moving the dx up here and the 12x squared down there, and we get that. Then we're going to go back and we're going to start changing stuff in the original integral. The simplest way to get u in there is u, but it is firmly attached to that power of 5, so definitely, let's see, we'll highlight here. So that right there becomes u to the 5th. And then we substitute, instead of dx, we put the stuff that we just calculated. It is right there, u over 12x squared. And then anything else just gets straight copied. So in this case, x squared was just kind of hanging out. And then we cross our fingers and we pray to whatever god or gods we believe in that the x's disappear. In this case, do they? They do. We cancel the x squared up there and down there, and we just copy what's left, which is a 1/12 u to the 5th du, which is far simpler than any other integral that's on this page. 1/12 can come outside. U to the 5th du is one of the few things we can actually do. It's our power rule. Add 1 to the power, divide by the new power. So it becomes u to the 6th over 6th, but the 1/12 is just hanging out in the front. Multiply the 12 and the 6 to get 72. So we get u to the 6th over 72 plus c. And then as Dave pointed out, we better not leave a u in our final answer. So we just go back and we change the u into whatever we let u equal way up at the top, which was this 3 plus 4x cubed. So there's our final answer, number 7. Not mandatory, but if you wanted to, you could check any one of these by taking a derivative at the end and making sure that you get the original integrand. Sam? Yes. So if it doesn't perfectly do it, we need another technique or maybe a different choice for you. But this is not a cure-all. It's not going to solve every problem. And if there are still x's left over, we need a new path. It didn't work. Okay, here are some hints for choosing u. In each of the cases, I'm going to recommend trying to let u equal the stuff in all of these examples. So if you see some stuff to a power, you could try letting u equal the stuff. That's what we had here. We saw some stuff to the 5th power in this problem. If you see some stuff inside of a square root, give it a shot. Let u equal the stuff in the square root, not the radical sign, not including the radical, but just the stuff inside. Any power, it doesn't just have to be a square root, any radical. If you see sine in something complicated, try letting u equal that stuff inside of the sine or the cosine, or as Coleman pointed out, we know that secant squared is one of our few antiderivative rules. So if you see secant squared of something complicated, maybe let u equal that thing in the parentheses. If you see some stuff on top of e, give that a shot. If you see some stuff on top of any other number, give it a shot. If you see some complicated stuff in a denominator, try letting u equal the whole denominator. That's the problem that we did together back on page 58, right? We let u equal the x squared plus 1 because it was in the denominator, because it headed us towards 1 over u du, which is ln. 1 plus some stuff squared. What antiderivative rule is that heading us towards? That's looking like an arctan if we can somehow manipulate it. And then this last guy, square root of 1 minus stuff squared in the bottom. That's looking like an arcsine if everything works out, right?
What do you do to combine them? I can't just add them together?
Yes, just add them together. In this case, it'll be a subtraction sign between the two of them. Yeah. And the reason that that Caitlin and I decided to put the two of them together in one fraction here was just so that we would be clear that just because you're doing a u substitution on one piece doesn't mean it affects the other piece. And so we completely separated off that 3 over x squared plus 1. I mean, you could, like, right, this could have become This could have become a 3 over u, right? We let u equal the bottom, but the du wouldn't have worked out on that one. We needed this x up here. That was important for us, and there isn't such an x over here. And so we just put this example in to show us that just because you do a u substitution doesn't mean it has to apply to the entire integral. And oftentimes splitting integrals up with additions and subtractions is the very first thing to try. Yeah. Mm-hmm. You absolutely cannot do it. Yeah, it's because it's a variable that you can't do it. Like what you're trying to do in your mind is say that this is equal to 9x times the integral of 1 over x squared plus 1. And you cannot pull that x out. You pull the 9 out, but not the x. And so as soon as you see that there's still an x up there, it is not arctan, because arctan has to be a 1 over x squared plus 1. Can't be anything with a variable upstairs. Okay, next page. We just did the walkthrough. Number 5, there are no hard and fast rules as to when u substitutions will work. Note that sometimes there's some trial and error involved in the choice of u. This is normal and expected. You should expect some false starts. Sometimes you just can't see ahead of time what choice of u will work. How do you know that it didn't work? You'll still have x's left in the integral. All the x's won't magically disappear. Let's try it here in number 6. It says this technique doesn't always yield the tractable integral. If you end up with both u's and x's in an integral after you substitute it, then the u substitution you just tried won't work. Let's give it a shot here. One of my recommendations for choice of u is if you see sign of something complicated, try letting u equal the complicated thing. So what's a good choice here? X to the 4th. It's the stuff inside of the sign function. U is almost always going to be the stuff inside of something. Next thing we do is we take a derivative with good notation. It's important not for notation's sake, but so that we actually have something that we can manipulate and solve for dx. So you start off by writing du dx. You can choose as much as you want. Absolutely. But suppose that you let u equal the whole thing. Don't write this. Then what rule do we need to do when we take a derivative? Product rule. So you're going to get this big massive thing, which will also involve cosine. And you're going to look over here and hope that magically the cosine that we just built is going to cancel with something that's in the original. It's not. So the more complicated you make that, the more complicated stuff is needed here in the beginning to cancel the stuff that you're about to build. Yeah. You can. Yeah, you can. We're going to do some of those next class. Yeah, good question. Okay, so we're good here. We're then solving for dx. So what does this become? Move the 4x cubed downstairs, move the dx over on the other side. Okay, and now we're going to start substituting carefully. This is an important piece of the process. You get the u in there as minimally as possible. U was x to the 4th. I see an x to the 4th, but I can't just write u. What is that u inside of? Sine. So that's the minimal stuff that I need to write to get u inside of there. Right? Don't write anything extra. Just get the u in there, bare bones. Then we replace the dx. In this case, dx is du over 4x cubed. And then we write down anything that hasn't been substituted yet. What is left over is the 2x. That's the only thing that hasn't made its way over to the new integral. And then we cross off all the x's. One of those goes away. Still left with x squared here. And that's the end of the ball game because there's still x's left in the integral. You can't do anything else. U's and x's do not play nicely together. It's either all x's or all u's, but not a combination of the two. So what does it mean? It means that this technique didn't work. We could try a different u. Honestly, I don't see a natural other choice for u or some other technique. We don't have another technique for this guy at this moment. We'll have more techniques soon enough, but this one is one of many that we cannot do. Okay, so here's my Richard Simmons encouragement moment. Finally, note that u substitution doesn't always work on the first attempt. If at first you don't succeed, you are not necessarily a failure. See how I keep my options open here? Like you might be a failure. Such a mathematical thing. It's like I don't care about your feelings. You might be a failure, but not necessarily. So you're going to keep at it until the integral whimpers in defeat, but you are going to have false starts, right? It is part of the process for U substitutions. Okay, so activity starts on the next page. I'll read this part here in bold. One of these integrals on this page cannot be done easily with the tools that we currently have. So if you get to one where things just don't seem to be working out, it could be that you have found the one where things are just not going to work out and we can't do it, all right? But I'm not going to tell you which one that is. What's that?
Just didn't choose the right path.
This number 6 is not doable.
Oh, it's not. Okay.
Not doable.